Last month on the PEDcast, we attended a spatial datasets event in Newcastle.
Lots of people are just not studying the Earth the way they used to.
Nick Skinner talked to us about workplace relationships.
They get those relationships to the point where I can juggle them really smoothly, and if I drop them, it won't smash.
Grant Campbell gave us a profile of his research.
Every day you learn something new about your own research, and I actually find that quite enjoyable, and it stimulates me.
And I spoke to Professor Daniel Batcheldor about his project to cultivate a soil on Mars.
Can we make a soil out of Martian regolith?
This month, I speak to Kyle Collins, an early career researcher working on the Mars project. Professor Mark Reed gives us another tip to improve our research impact. And Ratan Lau, the president of the IOSS, delivers his first monthly address for the PEDcast. We know that soils function better when they're aggregated. And it's the same for soil scientists. That's why there's so many soil science societies around the world. One of the most widespread is the International Union of Soil Science, with a diverse network reaching all over the planet. Ratan Lau is the president of the IOSS, and has very generously agreed to record a monthly message for the PEDcast. Here he is in his inaugural broadcast, talking about the hidden treasures of nature.
Numerous attributes of soil vital to essential ecosystem services are hidden beneath the surface, and are neither obvious to casual observer nor easily comprehended. It's a classic example of out of sight, out of mind. Several environmental problems of the 21st century have arisen because humans neglect, misuse, take those precious resources for granted and treat them as the global commons. Examples of ignored resources include soil organic carbon, the soil water storage capacity, and soil microorganisms. For example, estimated to 1 meter depth, the global soil organic carbon stock of 1500 petagram, that's billion metric ton, is 2.4 times that of the vegetation, 630 petagram, and 1.9 times that of the atmosphere, 800 petagram. While the biomass of trees is visible and appreciated, the hidden soil organic carbon stock is largely unknown and therefore ignored. Most cropland soils of the Midwestern region of the US contain, for example, 100 megagram of soil organic carbon per hectare. Each megagram of diesel or oil being equivalent to 1 megagram of carbon, soil organic carbon stock in 1 hectare is equivalent to 100 megagram of diesel or oil. Similarly, it is the soil water storage capacity, the so-called green water, on which depends the Earth's net primary productivity. An ideal soil, 50% porosity containing an equal amount of water and air, contains 2500 cubic meter of water to 1 meter depth, which is enough to meet the water needs of 25,000 people at about 100 liters per day. 1 tablespoon of a fertile soil contains billions of organisms, including bacteria, protozoa, nematodes, and fungi. These organisms are essential to recycling of biomass and are source of antibiotics and other ecosystem services. The fact that even a well-meaning administrator, policymaker does not consider these and other attributes of soil in conceptualizing a development plan or a program is indicative of the lack of communication between soil scientist and the decision maker. Addressing the out of sight, out of mind syndrome necessitates a strong and continued communication between soil scientists on the one hand and research managers, policymakers, the general public, and land planners on the other. Indeed, soil science community has an exciting but a challenging task as researchers, teachers, and communicators for enhancing the awareness about the importance of soil to human well-being and nature conservancy. As the Dalai Lama said, the roots of all goodness lie in the soil of appreciation for goodness. Thank you.
Thinking about our soils is a bit like baking a cake. The quality of the cake, its taste and texture, will depend on, for example, whether you've used the right kind of flour. And there are, of course, many different types of flour. But whilst the cake fanatics debate over which one is best, there is something that they all agree on, and that's that you need some type of flour. It's the same for the functioning soil. There are a whole myriad of biological, physical and chemical properties that may constitute the perfect soil with these classic horizons. The bedrock layer, the saprolite layer, where the bedrock is weathering, the subsoil, and then finally the topsoil. But at the end of the day, the soil material is the most important ingredient of them all. But the formation of soil material is a long and slow process and starts with the bedrock. If you were to place a piece of rock in your hand, it may not look like it's changing at all. But if you were to sit here for 1,000 or so years, you would start to see some extraordinary changes. In planet Earth's basement, the bedrock is slowly breaking down physically and chemically, turning into what we know as soil. The cake that we saw earlier allowed me to demonstrate the various layers in the soil profile. And I've come to Hale, the most southerly point in old Lancashire, where we can see that in reality. So here's the bedrock. The sandstone, which is weathering into the saprolite, this material that we can break off in our hand. But we're not just forming soil, we're forming quality soil. And you can see just in colour how that quality changes as we go up the profile. We can start to see how the reddish of the sandstone turns into the light brown of the subsoil, and then finally this dark organic horizon at the top, the good stuff. So I'm going to go up there now to see this quality soil. Soil formation takes a very long time. Studies around the world estimate that only 0.04 millimetres of soil are converted from bedrock each year. That's the width of an average human hair. Although it takes a very long time to form, it doesn't take very long for it to erode. Whilst it doesn't look mobile, soil is on the move. It erodes down slope, some entering watercourses and some eroding into the air. Where these rates of erosion exceed the slow rates of soil formation, the soil is thinning. At one of my study sites in Somerset, the thickness of soil ranges from 1.2 metres to 3 metres. But what does this mean for UK soil sustainability? How many years do we have until our arable soils thin to such an extent that they become unproductive for farmers? These are the questions that I'm investigating as part of my PhD. One of the most important things to know is the rate at which soil forms. My project will conduct the very first rates of soil formation on UK arable soil. In fact, given that most of our existing knowledge on soil formation rates stems from studies done in the world's most mountainous areas, it will be one of the first studies in the world to calculate rates of soil formation on farmland. If we know the rates at which soils form and the rates at which it erodes, then we can start to think about the current lifespans of our soils. We can begin to evaluate our soil erosion rates, not based on which one's the greatest, but based on how much greater they are than our soil formation rates. The question then becomes, how can we extend the lifespan of our soils? Curbing erosion is clearly one strategy, but we may also begin to think about the ways we can speed up soil formation. The good news is that we've already begun to think about this too. And if you don't believe me, take a look under the lid of your compost bin. It may not be the most glamorous sight, but it could just inspire us to think creatively about how we can extend the lifespans of our soils and conserve them for future generations. Time is of the essence, and perhaps that's no more true than for researchers. Finding time to do anything is often tricky in our busy lives, and many of us may say we haven't got time to achieve genuine research impact. Professor Mark Reed is from Fast Track Impact, and he believes that we can do just that, fast track our research impact. So here he is now, with his tip for March.
One of the main objections that I get from researchers who are thinking about engaging in impact is, well, I want to do it, perhaps I feel I ought to do it, but I just don't have time to do it. I think that tackling that issue head on is crucial if we are going to enable and empower people to actually follow their heart and engage with people in the outside world to make a difference from their research. And so one of the key things that I encourage people to do is to plan for impact. If you plan effectively for impact, then actually that empowers you to now start to filter out the things that actually are not realistic in terms of your time or your resources, and start to much more strategically narrow in on, well, here's something feasible, here's something I could do, here's something I feel I've got the skills, the confidence to do, great, this is actually something that feels okay to me. And a crucial difference now is that rather than hoping that you're going to have an impact, worrying that you're not having an impact, you have a plan that is feasible and you can actually get it done. And actually, the evidence suggests when you have a plan like this, it actually does happen. So, crucial to make a plan. The problem that people then come up with is, well, okay, but if I'm going to make a plan for my impact, I kind of need to know what it is that I'm trying to achieve. What is the change, the difference that I want to make? And actually, I, to this day, find this one of the hardest things. Coming up with a really clear, persuasive impact goal is actually a very hard thing to do. And it's not something we're typically trained in how to do as researchers. If you can crack this, however, in terms of your funding proposals, actually increasingly having a very persuasive and impressive feasible impact goal actually can really crack the funding for you as well. So it's really great to get this. But for me, if you're struggling with this, the first step is not to ask what impact do I want, but instead to ask who's interested in my work. And I've yet to find a researcher that can't answer me that question. Someone, anyone other than your mum, who might be interested in your research. And it may be a professional body, it may be schools and the curriculum, but someone somewhere who would be interested in your work. And once you can understand who that person is, maybe you even go and speak to that person and really explore why it is that they might be interested in your work. You can work back from that interest to say, well, why is it they're interested? What do they benefit from that? And now you have a kind of a prototypic impact goal. If you take that and then you say, right, well, what kind of activities could I do with these specific groups that would actually give them more meaning, more value, and really help them to dig into that interest and get some benefit from it, it starts to become clearer. And then come up with a couple of indicators. So you might think of some activity indicators that would tell you whether those activities are actually working or not, but also some impact indicators. So how would I know that they had benefited or not? Then it starts to get even clearer. And one final step that I take is I ask people to identify the means of measurement. So it could be qualitative or quantitative, but how would you actually be able to tell me very clearly that yes, that benefit had happened? And if you're really struggling at this point, I tell people to just to close their eyes and say, well, what can you see? 5 years from now, what does it look like? What would you hear? What would people say to you? And actually at that point now, it becomes that bit more concrete. And so you end up in a situation where you can revisit that impact goal and you can turn it into a SMART goal, which is specific, measurable, achievable, realistic, timely. And that then becomes the kind of goal that can power you to some really impressive impacts with a plan, a bunch of activities for specific groups that you know are going to really work. The final step then is, well, I've got a bunch of these different stakeholder groups, publics, I've got a bunch of different activities, and I'm now strategically looking through and working out, right, these are the ones that I can do. I've got time to do, I've got resources to do, these are the ones I'm going to prioritise for my funding application, these are the things that I'm going to try and get done by the end of my PhD, and this becomes something practical.
Last month, I spoke to Professor Daniel Batrador, all the way from Florida, who's working with NASA about a project to grow soil on Mars. The project has a team of scientists all over the world, and one of those is early career researcher Kyle Collins. I caught up with Kyle this month and began by asking him how he got involved in the project.
So I just kind of completely stumbled upon this project by just kind of by chance. And so I knew coming to college that I wanted to do something, get involved with getting to Mars and somehow. And so one thing that FIT really stresses is undergrad research. And as an undergraduate student, going to the faculty and asking around for different research projects that are being done at the school. So I went, when I was just touring the school, out to the department head and asked him if there was anything, that he knew, that might have something to do with chemistry in Mars. And he just kind of pointed me at, well, there's this regolith thing that we're doing. And which at the time I had absolutely no idea what it was, I had no interest very much, but since then I just kind of started picking it up, and it's been really fascinating.
And you've been thinking about regolith on a certain planet, Mars. I mean, why Mars? Why not Venus or Jupiter or any of those other planets?
Hopefully soon. I mean, much like how we went to the moon, I hopefully view Mars as just a stepping stone to get further out into the outer planets, or even past our solar system to Alpha Centauri, just beyond our known universe. But got to start somewhere. So Plus, Mars and Earth formed at very similar periods in time under very similar conditions. And so going to Mars, hopefully if we get to Mars and we can understand more things about Mars, then maybe that'll help us understand about things about Earth and Earth's history, Earth's future, and such.
And you mentioned the moon. Perhaps someone thinking about the logistics of going to other planets or other celestial bodies might think that the moon it must be easier to go there. We've been there before. We know a bit about the Martian regolith. Why not produce some sort of soil on there?
Well, we do. We have lunar soil here on Earth that astronauts, when they have gone, we have it that they brought back that we've studied. And there are companies who have basically replicated that in a lab and created like a synthetic lunar regolith. And so we do have samples of them. We are studying that as well. But the biggest reason to study the Martian soil when we try and do these manned missions to Mars eventually, to know what we're dealing with and to give the astronauts who land there an edge.
When the Martian scientists, and you may well be one of them, land on Mars, they will need to survive, and obviously they can't take things with them, so they're going to need to grow, presumably food on Mars. And I suppose in that sense, food and water and what we need to produce those kind of resources, soil at the end of the day, it's the soil that's one of the most important resources.
Yes, and that is one of the biggest ongoing concerns and biggest fields of study right now is ISRU, or in situ resource utilization, and using what we have on the planet, because it's very expensive and takes a lot of time to get things to Mars. The window for travel is very, very brief, and so you have to be able to use what's already there, as well as what you take with you on that first trip. And so there won't be very many resources at first. And so we're studying the Martian regolith to hopefully try and get a better understanding, like I said, of what it's like out there, so more prepared and can use what they have at their use their resources that they have available to them to the most maximum effect.
You're working as early career researchers with researchers from experts around the world, and obviously at the Florida Institute of Technology. But this is a project which anyone can get involved with, any early career researcher, or possibly the public as well. And it's through those citizen science initiatives, isn't it, that really make those kind of things happen. So how does citizen science come into this project? Because it obviously does to some extent.
So like I said, we're trying to analyze soils from all over the world, and we can only be in one place at a time. And so citizen scientists are exactly how we're going to be able to gather this soil from all over the world to be able to study. But basically, we'll send you a vial, very similar to this one. If you think you are in an area, get in touch with us. We'll send you that vial with the address and how to get it back to us, and you can get it back to us. And when we finally come around to be able to publish this paper, you'll be put on as a co-author and a co-publisher for these papers.
So if people want to get in touch generally about any information they wish to know about the project, perhaps get into touch if they want to land on Mars, or they want to be in that space shuttle that goes up to Mars, and who knows when it might be, next year, 10 years, 20 years. How do they get in contact with you, Carl?
So if you want to get in touch with me, I'm always very easily to get in touch with. My email, kcollins2016@my.fit.edu. You could easily get in touch with me through that. If you just want general information about what's going on, you could go to the school website, Florida Institute of Technology, and that's the best way to just kind of find general updates and information about just the whole scope of the project that we're working on.
Fantastic. And here at the British Society of Soil Science, we wish you all the very best, Carl, in the project, and we will monitor your development closely, because who knows, you know, we were talking today, March 2018, but it could be March 2028 where we see you finally lift off to go to Mars and to create some soil on the red planet. Who knows? But
that would be incredible.
Well, you know, hopefully we can dream big dreams. Thank you, Carl, and it's great to hear from you. Thank you.
All right, thank you.
Well, that's about it for this month's PEDcast. I do hope you've enjoyed it. If you've got any ideas for the next programme, don't hesitate to contact me on the address below. Next month, I'll be in Vienna with a special feature on the EGU. But until then, have a fantastic April. And from me, Daniel Evans, goodbye.